start recording. Hopefully everything is hunky-dory. Right, so where we left off, we had this little thing that drew some lines and a triangle and some lines. And I think the direction we discussed, I'm not sure we discussed this on stream, but we were probably going to sort of go in the direction where we were going to focus on like physics and sort of the heavy math stuff. So we were going to probably move towards making like a simple pinball style game, I think was what we decided. And we'll see how that goes. And so I've just been doing this line rendering stuff and talking about how to render triangles and things. And obviously we've been on break for like, what, 3 weeks now? So just refreshing what we're doing. So what I want to do, and partly because this sort of feeds into the physics stuff that I want to do, is spend a lesson talking about pixel shaders, because I mean that's just important in and of itself, but also it gives me a few opportunities to talk about stuff that then I can call back to. So it's all nicely planned like that. So what we should do is we've got this big game, and I don't know how long yours is, but mine's like 400 lines long, and it's got all this line drawing stuff, and we don't need any of that immediately. So that's actually I think my secondary one, with all the super secret stuff in. Let's make a new class. Add new item, new class, and we'll call it shader test. That'll do. And we'll derive from game in not monogame. What is it? Derive from game in. Let's grab all the usings from that and derive from game. There we go. So basically we're starting from scratch. So first of all, we need to initialize this thing. So we'll pop over to program and swap out that type with our new one. And then we have to basically remember what we need for like a do nothing game. So if we reference back here, what we need is a graphics device manager and a constructor. And I'm pretty sure we just need what's in the constructor. And change the title. Everything else is fine. And then we just need to override load content and draw, and why not update as well. And kind of like to keep these things in order, so I think we normally put draw at the end, so we'll put draw at the end and move update just for fun. All right. So, and then all we need to do is graphics device.clear color dot, I don't know, pink. And in theory, if we run this, okay, we get the new screen. So we basically cleared out all the old stuff, just so we've got an easy base to test on. All right, so now for people playing along at home, I'm just going to quickly plug FNA Template. So this is just a quick thing that I made, and I think I've plugged it before, and it's sort of the source code that we're working from. It's basically FNA with a bunch of stuff that makes it build shaders and things. So this is the URL now, so I'm sure I'll put a link in the description if I remember. So what we want to do is more or less go back to what I had as the template game, which was basically we have a sprite batch and an effect and a sprite. So we're just going to bang in a sprite batch and a texture 2D for our example sprite. Actually, we'll call it smile because it's that in the template. So I've also not programmed for like 3 weeks, so it's like new sprite batch graphics device simple as that. Smile is content.load, takes to 2D. And then I'm just going to splat that out to the screen. 2020 and color white. So in theory, yeah, and we get our smiley face.
Oh god.
That's cool.
What's there?
So this is sort of just our starting point. So basically we're going to use this as a way to go through pixel shaders. Have you got an effects directory? What's in your effects directory? Because I know we were just talking about this before we started.
Just a test effect.
Okay, so you do have test effect. I think mine's called example effect, and it's exactly the same. So maybe
I'll just rename mine.
Yeah, rename to example effect. So yeah, for the viewers, Daniel's working off a copy of the template from before it was released, and I changed the names of it, pretty much everything. Okay, so let's apply that to our thing and see what it does. I mean, it's fairly straightforward. So
does it need to be in content though? I don't think it's in my content bag.
No. Okay, so let's have a quick word about the template. The template does everything through Monogame's Content Builder except effects, because Monogame's Content Builder doesn't have a good way of doing effects. So if you hit F4 on the effect, you'll see it's using this build action compile shader, which goes off to use the shader compiler from the DirectX SDK. Which reminds me that what I was about to do is going to be, I was going to go like, all right, and now we do it same as old XNA. It's like example effect equals content.load, blah, blah, blah. And that doesn't actually work here. For reasons that we chat about in the template, we need to actually just copy this line. Basically, new effect equals file.read_bytes from the output of the effect builder. So it was an FX file, and then its output is an FXB file. So in theory, that should work. So
okay. So this is pre-compiled using like that Mojo Shader stuff.
So what happens?
The compile shader is the build thing, and then
yeah. So
okay,
this gets compiled with the DirectX shader compiler from the DirectX SDK. So that converts the FX file to an FXB file, and of course that could be used directly in DirectX 9 or whatever. But obviously we're using FNA, which uses OpenGL. So what Mojo Shader does is it takes the compiled shader and then converts it to GLSL shader thing, and then that gets recompiled again by the graphics driver to a shader that's appropriate for the graphics card. So there's like a bunch of extra steps involved, which is a bit unfortunate. But on the plus side, the reason Mojo Shader is nice is because it will take this one FXB file and it will output appropriate shaders for like every platform. Well, all the platforms it supports. So it does, I think, at least 2 versions of OpenGL and like the mobile GL. Was it
CLES?
Yes, that's what. Yeah. So it'll do like your phone shaders as well, all off the one file. So we've still got this thing. So we need to actually use this shader now. And I'm not sure we've talked about this yet, but there's a version of the begin function that takes an effect, and so we can just pass in.
We used it before.
Yeah.
We used it for the basic effects. But we haven't done any passes yet. Is that a problem?
No. Okay. So that's
no.
Yeah. Sorry. 4 nulls. So there's four render states, and then the effect, and then after the effect comes the transform. So let's hop into the shader code, and now we have that working. Let's have a little talk about what it's doing. Where did I put the shader code? Example effect. Okay, so unfortunately we don't have. Can I get some highlighting? Open with Notepad. So I've actually got some highlighting. Come over here, highlighting here, which makes it a bit nicer. So let's talk about what's happening here, and I'm just thinking, what's the best way to do this? Okay. Can you, if I wave my mouse over this, can you actually? I'll do it. I'll do it the good way. I'll up the production values, and we'll go over to the whiteboard, edit, and paste as new layer. Okay. So. Yeah, I know. And expand. Layer to image size. Oh, whatever. That's what I wanted. Okay, we're good to go. We are good to go. Right. So this kind of looks like C code and obviously C# code, so it should seem fairly familiar. So this pass thing we have here, that should be familiar to from what we were doing the other day. So that's sort of the entry point. I'll just bring up the code we had the other day, and I'm glad you mentioned it because that's important. So when we were drawing triangles, where is it? Yeah, for each pass in current technique passes. So this is just deciding what the shader is going to do. So you choose one technique in your code that uses the shader, and then each technique can have multiple passes, and you don't have to use all of the passes, like pass 2, etc. You don't have to use them, but well-written code that sort of will accept any shader, I guess, will have this loop in it that will use all the passes and from one technique. And this specifies, this is the pixel shader we want to use, and then, we're going to compile a pixel shader. That's simple enough, and it's going to be this shader model. So the different shader models have different features. So as you go up, it's probably not really that important, the details of this. As you go up in shader version, the shader functions can be longer and can have more features, like you can use loops and stuff. The shader compiler, if you write some code in your shader function that doesn't work in a particular shader model, the compiler is just going to say error, like we can't do this. So often that will be because you wrote I guess these days it doesn't happen because it's like what are they up to, like 5 or 6 or something, much more than 2. But back in the old days, you were limited to like a certain number of instructions. I wish I had the decompiler handy.
But we kind of had this problem anyway in River City, right? Because we had to use this because we needed to get on different devices. Did we not? Like we had some considerations to make about like particular effects that we had that had to do with the shader model.
Yeah. Okay, so we were on XNA, and where's my thingy? Why is this misbehaving? Here we go. Come on. Okay, so we were on XNA4, which has two sort of graphics modes. It's got reach, REACH. You can read that, and it's got high def.
Right, and we were forced to use Reach.
Well, no, we supported both. So this, from memory, because it's been such a long time, this is 2.0 shader
That's
model,
right. Yeah,
and this is I think 3.0, but it might
3.
do like 4.0.
I thought it was 3, but I don't know enough to know if I'm right.
I don't even remember.
Pretty sure it's 3, but only because
Yeah.
I've seen errors.
Okay, let's pretend it's just three.
Just say it's 3.
I'm going to take your word for it. Like the documentation exists for this. Look up XNA4 and these two keywords, and you can find like a table that looks like this, but with a bunch more stuff in it. Anyway, so yeah, we had the pixel shader that did the palette changing. We had a version for high def and a version for reach, and what was interesting about that is when we went to draw, like say we've got a dude or a scene, like I think this was an effect that was applied after the scene was drawn. So we've got a happy little scene, and so I don't know, it's got some colors in it or something, and we wanted to apply like a colorization filter. So the 3.0 version, what it would do, it would take like a color cube, and what that was is it would, this little bit of the cube is black, and this bit up here is the certain color of green. Well, actually, it's a cube, so it would have 3 axes. So it'd be like green, and then like red, and then I'm probably getting these mixed up, and then blue. So that corner would be black, and this other corner would be, it's ridiculous to try and draw it, but this other corner would be white. And then this corner, say up there, would be red, and we're actually going to see sort of something that looks a bit like this, and like this corner would be green, and so on. And like in behind there, you can't actually see it from this angle, that would be blue. And what we do is we use that to map colors in a lookup. So if we took a green color here, so this bit of green, we look this up in this cube, we look over here, and this cube could specify a different color. So it could be like, oh, we want all of the green to turn purple, and so it would look up a color like that. Or in fact, let's do it closer to what we actually did. It would be like this sort of dark gray faded green, because we mostly did this for like screen transitions and fades and stuff. And so then when we went to like draw this scene, it would output something like like that, without slightly grayer green, and then obviously the blue, maybe it was like a grayer blue, and so you get that. And that's how we did screen transitions. But this operation here, where you look up from, we start with this texture and we look up into a second texture based on what we looked up, and then we output that, that's not available in 2.0. That's only available in 3.0. So for all of the people who had really old graphics cards that only support 2.0, we did something else. We had a basically a pixel shader that took the incoming pixels and applied just a straight up mathematical transformation. So if your red curve before was like just 0 red results in 0, and like 100% red results in 100%, we'd do a thing where we faded that out with like that. It was actually a bit different because we adjusted contrast and stuff, so like 10%. And then that would spit out an image that was similar to this. It didn't look quite as nice because it didn't have the fanciness of this method, but it was good enough for people with not so good graphics cards. So that's sort of what the shader model does for you. Is it lets you do you need newer hardware to do more stuff, basically.
What I really like about this is that, like, the whole point of that feature was to get like an old school like fake like transition, right? You're fading your opacity, but we didn't, we made it so we could never use the alpha channel, so that it would be more, we had exactly as many fade steps as the Nintendo had. But it's just interesting that we can't do the old school effect on the old hardware. We have to do the bad effect on the old hardware, and only the new stuff can do the old stuff.
That's very true. I like that a lot. So that's basically the difference between the shader models. So this is obviously Pixel Shader 2.0. And then we have Pixel Shader function. Let's come back in. Let's go back into color. Let's not fade out. We have Pixel Shader function here, which is obviously this one here. And so this is basically defining the entry point. So like in C and stuff, we have, main. This is like, where do we go first? So we can have more functions in there, and we can call functions like this is not strictly speaking a function, but you can call them as you'd expect. So this tells it what function to call, and then we have, well, let's go through this function. So it should look like a normal function. We've got this interesting thing here. We have this float 4 data type, and so that's just a built-in data type with 4 floating point values. So in this case, exactly, it'll be R, G, B, A. And if this was a like a 3D position, that'd be X, Y, Z, W, and these are basically interchangeable. You'll notice here that I'm accessing texture coordinate X, and unless I'm horribly mistaken, because it has been a little while, you could also write text.r, and that would be the same thing as writing text.x, because it's the same data basically, and so that's just for convenience. So we have this data type, so that's the return type, and we have these arguments which also float 4. So we've got a color coming in, and we've got a texture coordinate coming in. So what's new and exciting and interesting here is we have this sort of color 0 and texture coordinate 0 and color 0, and obviously this one, you can see this one's outside the function. So this one here is the register for the output, so for that one, whereas that one is obviously color, and that's text coordinate. So these names are obviously arbitrary, but these ones are the registers for where the data gets sent around the graphics card. I think we may have mentioned this before. Is this sounding familiar?
Yeah, except the terminology on register is a bit lost to me, but I mean, index buffer, vertex buffer, I can't exactly remember. The register is just the location, or?
That's right. So we did, whoops, touch off. We did talk about this actually, now I remember, and so we had this thing here, and then we were talking about we had to define a vertex declaration, and then we can go to this vertex declaration, that's the built-in one, and it says blah 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 static constructor. So the first one is position 0. This second one, is offset by 12. The format is color, so that's just what the format is. But these ones, the usage, color 0, that maps to this color 0 here. So that's how the data comes in.
Okay.
And there's like a limited number of this, and I believe, and in fact I'm almost positive that the number and types of registers available also depends on the shader model. So newer graphics models have you can pass like 10 texture coordinates in if you were so inclined, whereas older ones maybe you could only pass in 1 or something. I can't remember the exact numbers. There's maybe we could look it up. If Microsoft still has that documentation for us, let's have a quick gander about DirectX HLSL registers, register binding in HLSL, and then okay, so you can see here this is the language, the syntax, and so this is like there's a colon and then the register, and then you specify which one you want. So this is obviously Pixel Shader 5, so it's like not as tidy as it used to be. Where's the old documentation? Actually, no. Sorry, that's something else. Register something else. or is it now something else? It's not. Oh yeah, no, sorry. Registers for the sampler. What am I thinking of? I've lost the name. There's this other thing that I want to bring up. HLSL intrinsics. So these are like the built-in functions. So you'll notice I'm using this text 2D here, and that's text 2D.
Yeah, this is like, I'm assuming is a magic function because it's not anywhere else in your code. So it's like a API level stuff, right?
Mm-hmm. And so what you'll notice on this right-hand column here is this says minimum shader model. So this text 2D one, obviously looking up a texture is very fundamental. So it is, where's it gone? It's obviously shader model 1 with this footnote. Whereas this one, which specifies a partial derivative, which I believe is used for MIP mapping. I think we discussed MIP mapping last time. That requires shader model 2, obviously. And then with level of detail, that's shader model 3. And so on. So there's all these methods. And so if you want a particular function, for example, actually no, 3D texture lookup is actually available in one, but doing it from one text to another is not, as we're talking about. What was I doing? I was trying to find the particular thing about functions, actually. So this HLSL reference is obviously very useful, and particularly that list of intrinsic functions, because it's like, well, I want to square root. What are the, how do I do that? So if you're writing shaders, that's this. You almost always have this up. I'm just going to quickly have a quick gander of this. It's going to tell me. Sorry, not register, semantic. That's the thing. The optional string, the intended usage of the data semantics. That one. Semantics supported in DirectX 9 and later. So here we go. Here's the list. So we've got color. Okay. N is the color you specify. Normal, position, tangent. You can have different outputs and inputs. So color, position, text coordinate as output. So the way these used to work is there was literally a register. Actually, it's probably not true because it was. It's probably always been this way, but there's sort of the idea was there was literally a register in the graphics card that you would put the color output into, which is why there was a limited number. These days, it's GPU is basically a general purpose processor, so the idea that there's actually a real register for these things is not necessarily true, and obviously, NVIDIA and AMD don't really tell you exactly what's going on in their GPUs, so you sort of get this sort of fuzzy look at what there is. Anyway, and then in these newer versions, there's DirectX 10 and newer, so they have system value semantics, which are a little bit different. Anyway, so those, I don't think those are supported by Mojo Shader anyway, so we don't need to worry about those too much. So the whole point of that is this color is coming from the thing, so that'll be like the when we pass that in, we passed in dot these text coordinates. They'll be, we talked about this as that's text coordinate 0 and that's 1 and so on, 1, 1. And then the output color will be like the color that gets basically drawn to the screen. And then we have the actual code of the thing. So we have text coordinate. Let's see. Sorry, we have a text value. So this is obviously an arbitrary variable name. And we're taking the text coordinate we got passed in, which is these ones. And we're using that text coordinate with this method here to look up in our texture sampler basically the color at that position. So it's going to get a texture coordinate like there, and it's going to go and look up into this texture sampler, what that color is. And you specify this with, sampler, texture sampler, register sampler 0. And so I think we may have gone over this one as well. No, we didn't. Not in that much detail, because that was handled for us in this old code by, we just said, where is it? Where? We passed a texture in for the thingy. Here we go, yeah, so line effect texture. So what this does is that will actually, when this gets applied, it will go off the graphics device to go graphics device dot textures, and then textures is a collection. So you can say textures 0, which will be this sampler 0 here, but you could also be like textures 1 or 2 or whatever, equals content dot whatever, smile dot the thingy that we're doing over on the other side. And so that's how you get like multi-texturing happening, is if you have more than one texture, you can sample from more than one at once. Okay.
Mm-hmm. Basically, like a lot of it is like, I'm just understanding it is, like a bunch of repointing. You have these functions and passes, and you're basically just telling the GPU what to do with this one pixel at this one texture coordinate, where you have one sampler for this. It's got the texture, it's got the place it is, and then you're basically going to do a functional programming on that to like manipulate what the pixel ends up being, right?
Pretty much, yeah, pretty much exactly that. So let's finish up with this last line here. So that's sort of all the nuts and bolts of just doing a pixel shader. And we'll talk about vertex shaders next, because that's not that tricky, but it's useful to chat about. So done all of how it actually works. This is sort of the line, I guess, where we're actually doing something of our own thing. I mean, I guess we're doing it here as well, but we're actually specifying our own stuff. So let's go back to the code and can I know what zoom I was at? Come back. Here we go. So let's look at this. What this is doing is it's taking the value from the texture we had before, and it's multiplying it by another color that is based on the texture coordinate. So let's come off to the side there and run. So obviously it's taking the color from the texture, that smile.png, and it's multiplying it by this other color, which is why you get this sort of blacked out area, because it's multiplied by black, obviously. The area that's multiplied by white is is being modulated by the texture coordinate. So the x, we're creating this float 4, so the x value is going to go into the red channel, and so as texture coordinate x increases, it's going to get more and more red. So that's going along this way. So as you can see, this is not very red here, and this is more red here. This would be more obvious if I actually get rid of the blue channel. So obviously blue was 0, and now I'm just going to change, sorry, blue was 1, now I'm just going to change it to 0. Reload that, please. Yes. So now you can get a better idea of what's going on. So yeah, I was on the wrong side. So starting at texture coordinate 0, 0, as the texture coordinate increases, it gets more and more red, and it goes to 100% red here. And as the y texture coordinate increases, it gets more and more green. And so that's literally that line of code. And then obviously 0 is like blue, which is why obviously I got rid of that to make that more clear. So does that all make sense?
Yeah. Yeah. I mean, sure. I don't see a visual difference. It might be my computer. I don't see a visual difference between 0 and 1 on the Z blue channel. I'm just gonna exit my Flux. Oh yeah, it's I'm using software called Flux to like make my screen very warm, and it was so orange I couldn't tell the difference.
Okay.
I just exited it, and it's like, okay, I'm not losing my mind. Mine's super pink and blue, and yours is totally red and green. Okay.
Wow, yeah, that you must have had that cranked right up. It's got that like
It's all the way up, yeah.
yeah,
Candle incandescent setting. Yeah.
yeah, the new version. I actually quite like it. I know a lot of people don't, but I like the super red late at night. Um,
I have it on that 100% of the time. Like I can't even look at a screen now.
um, okay, so
So just to
let's
be clear,
yes.
the pink in mine um has something to do with the pink color that we chose for the clearing,
No, no.
or
So I
that's
mean,
just math. Yeah, that's just basically because you're increasing red and green as the texture coordinate is changing, and that's why, and that's all you're doing basically.
yeah. So I mean,
But when
and
you're
yeah.
the blue is what was
So
right,
I
right.
I can stick this in here and add a bit of transparency, and you can see it fades out.
Yeah,
And
makes sense.
what can I do? I can make that super obvious by doing that.
So shaders are only like they can't be dynamic in the sense that they can only use the data that you're passing it, right? I mean, I think I've seen some pretty freaky shaders. So like when you look at shaders for light and everything, those are actually always going to be sort of a static or a single functional output, right? That there's no you can't do like animations and stuff in shaders, I'm assuming.
Oh, you can do all kinds of crazy stuff in shaders. What I think you're talking about is what happens is there's a pipeline in the GPU. I think I need another thing for this. There's a pipeline in the GPU. So you go, can I please have some color? There we go. Okay, so there's a pipeline in the GPU that you've got, and I'm going to simplify this a wee bit. So you specify in your program, I've got some triangles, and they draw some stuff, and I've got some textures of like my happy smiley face texture, and we feed those into first of all the vertex shader. And that's going to take these vertices and do something with them. Maybe transform them by the camera, like we've been sort of doing recently. There's also like what are they? The geometry shaders, and I forget what all the terminology is for the fancy shaders that will do more complicated things. But suffice to say, there's in newer graphics cards, there's some extra steps in, I think, here and here that do more stuff with the vertices. But anyway, so maybe we run a vertex shader and it moves our stuff around. And a vertex shader, I think in like version 2 or something, shader model 2, it can also it can read textures if you were so inclined, but usually you don't. Anyway, the vertex shader spits out its data to the pixel shader. So that's drawing a whole bunch of little pixels based on so over here, so it's drawing a bunch of pixels to the screen based on one of these triangles. Over here is like a fixed section of the pipeline. This is the rasterizer, and what that does is it says, okay, I've got a triangle here. Can you tell me, please, which pixels are filled by that triangle? And because obviously this is like such a what do you say, like it requires high performance, this particular process, because and not only does it require high performance, but it's not really that much you actually want to do differently other than just being like, I have a triangle, give me the pixels. So that happens in between the pixel shader and the vertex shader. The vertex shader and the pixel shader, is it decides which pixels on screen to draw, and then once it's decided, it will pass off those pixels with the appropriate inputs to your pixel shader. Then at the end of the pixel shader, what you have, and this is also a fixed sort of section of the pipeline, you have the blend stage. And this is the only point where you actually access the back buffer. So it's going to take these pixels that it drew, and it's going to, you've got your image, it's going to take those and slip them in there and overwrite the values in the back buffer. So what's important about this is you can't actually read the back buffer from the pixel shader. This is not allowed, whereas this one is a-okay. And the reason for that is because obviously you're not shading one pixel at a time. The GPU is actually running, hundreds of threads and shading possibly tens or hundreds of pixels at one time. And so the order in which pixels arrive on the back buffer is obviously a parallel programming issue. They have to be the writes to the blending stage. Sorry, the writes that the blending stage does to the back buffer have to be reordered. There's like just here. There's a what do you call that? Like a sequencing point or something. I can't remember the correct
defrag.
Sorry.
Sort of like defragging.
Kind of actually. That's actually kind of right. So it's going to have like here's a pixel and here's a pixel and here's a pixel and here's a pixel, and say this is the order they're supposed to come in, and they actually come in that order. That stage is actually what it's going to do is it's going to make sure that this one we're going to wait. We're going to say don't draw those three now. We're going to wait for this one that's supposed to come first until it actually arrives, and then we can draw in the correct order where like I guess time it's makes sense, so that when you're drawing one pixel here that's supposed to like have another pixel drawn after it into the same place that has like some transparency or something, that ends up looking correct. Otherwise you obviously get a garbled image. So obviously and part of the way the blend stage works to make this happen and to be fast, and I'm a little fuzzy on the exact details about why, but it's just the way it happens, and it kind of makes sense. Obviously you can do a lot in a pixel shader. You can basically write arbitrary code, whereas the blend stage is very fixed function. So I'll just show you what that is if I can find it. Actually, yeah. So it's the blend state. So state dot the BS, the blend state equals new blend state BS dot. So you see all of these things. There's actually not that much involved. There's basically you can do different things for alpha and for color, and there's some masking and stuff you can do. But it's basically color source blend is blend dot this algorithm involving like inverse destination alpha. So it's like, how much color do we want? We want as much as the destination alpha was, which probably doesn't make sense.
Where's the back buffer reference in this? Are we just implying that we're always talking about blending between the new pixel and the back buffer pixel, or how many layers is that? I don't really get it.
Okay, so the blend function is basically a function. I'll just bring up blend. You get it actually. Okay, so this actually tells you the exact blending algorithm. So this is all that's available. So whereas you could write arbitrary code before, you can only do this, and you can do what is it? I think is it BS dot. Oh yeah. So you can do a different function for alpha blend function. What was that? It's blend function. Oh yeah, so you can do a subtraction and stuff too. Anyway, getting to the point. Sorry, I've lost my train of thought. Basically, what happens is we have source. So, and this will be
Right.
Pixel shader is the source, and then we have destination, and that is either, you know, the back buffer or a
Render target.
render target. In some sense, are the same thing.
Right. That's how you can do like that's how you do stenciling, right? When you can like kind of take the render target and like punch out some of the pixels to make like shapes or whatever.
I kind of like, you could do it this way, but stenciling is actually a different GPU feature. Like it's a different specific feature that does that as well.
Okay, sorry. Oh yeah, that's a depth stencil thing. Yeah, okay. I'm getting it mixed. There's a bunch of stuff in that bag I don't quite understand.
That's the best way to draw this. So, and then we have, you know, blend mode. So, you know, the information comes here, and then so we're performing like some function. So, you know, like so if you know, this might be like alpha of, you know, destination. Actually, destination alpha is like, it makes sense in a very few circumstances. Like, so source alpha times the source color, and you know, so we apply, say, that much source color, and then I guess there'll be one for the destination, so it's plus, my box is too small, what is it? It's plus inverse source alpha is, I'm trying to do this from memory, because alpha source times color of destination, so that ends up looking like that. And you can see if you add those two together, that's like a really simple alpha blend. So as sorry, it's not one, it's inverse, but it's not 1 over, it's actually yeah, that was wrong maths. 1 minus alpha source. So hopefully you can see, does this make sense, that if as alpha increases, the amount of source color increases and the amount of destination color decreases? So that's how you get like a really basic alpha blend.
I mean, yeah, it makes sense intuitively. I guess I still don't quite get how you set the destination, but I guess in XNA you would just set it with some kind of like with the render target 2D or whatever.
Yeah, so that's device dot clear, you know, blah.
Right.
So that just sets it, and then that you spit that out, and that goes to, I guess, back to one of these ones. And this, the fact that it goes back is what makes it you know, yeah, that's what I mean. This process here, it needs to be serialized, so it needs not in the like data writing sense, but in the ordering sense. It needs to be in the correct order. And so this process is what makes the requirement for this need to be very fast and very simple, basically. So the one that I've just drawn, this one here, that is that's like alpha blend. That's like a standard alpha blend, although I think it's actually called something different. So let's go into the code, and actually, because we have FNA here, we can actually look at this, because there's a few built-in blend states, like state dot. So there's like 1, 2, 3, 4 blend states that you might actually use, and so alpha blend. So this is not the alpha. This is like the new style alpha blend. This is this is pre-multiplied alpha blend, and then
that's the old one, right?
And non pre-multiplied is the old one. So that's what I drew here.
Yeah.
And so it's just a little bit of maths that means that rather than this multiplication that's happening, oops, you can see that this function is multiplying by the alpha, Whereas,
Yep.
The 1 is obviously looks like that because that multiplication has already happened into the color channel. So I don't want to get into too much detail on how pre-multiplied alpha works at the moment.
Yeah. I just remember when we went from XNA3 to XNA4, everybody lost their mind because they changed it and nothing worked anymore.
I was
With
yeah. I was so happy because I ran into the problem that pre-multiplied alpha solves, and I'm like, all right, now I have to go into my XNA3 code and like jank it up to make it pre-multiplied, and then XNA4 came out and it's like, oh, it just works properly now. It's kind of surprising that like no one really came up with the like like obviously people knew, but it wasn't sort of commonly used until like super late in the process. Like I don't know when XNA4 was. It's like 2008 or 9 or actually probably more than that.
Yeah,
2010.
I think 2010.
Yeah,
Yeah.
like you'd think maybe by like 2004 or something that they would have figured that out, but no. Anyway, so that's pixel shaders, sort of in a nutshell. So then there's this vertex shader thing. So what's the best way to do that?
We'll probably leave that to next week. I think you said though you wanted to cover that.
Well, I wanted
next time.
to talk about circles as well. So I might let's leave vertex shaders until next time, and there's really not that much to talk about because it was basically like, and now we can replace the vertex shader. What were we doing? Oh, that's right. Because okay, so we in the shader test in this one, we're replacing the pixel shader of the sprite batch. So sprite batch comes with its own vertex shader and its own pixel shader. We're replacing just the pixel shader. Whereas over here, where we're using basic effect, if we replace basic effect, we actually have to bring our own vertex shader. And so that's actually almost boilerplate. I think this is it. Like, let's just go through this because it's so quick, and we won't actually even code it up at this stage, but we'll just talk about it.
Yeah, that's probably good because I don't have it in my bucket yet. I'll have to switch over to the good template.
That's all right. What did I want? I wanted paste as new layer. Close enough. Can I get some pretty background, please? No. Sorry, just bear with me while I hit all of the wrong buttons, like every single one of them. I don't know what I did. Paste as new layer, and then I need to come up with a better way of doing this particular process. Okay, all right. So this should be really like super familiar because we were just doing it before with the pixel shader. So did that come on screen? Okay, so we have down here, we have, as well as compile a pixel shader 2.0, compile a vertex shader 2.0. This is the vertex shader that we're specifying in the pass, in the technique, and this is the vertex shader function. So that's just finding our entry point for the vertex shader. So the pixel shader, more or less the same. Obviously, we're not doing that funny, like this color thing is just a straight up multiply, rather than like this is what sprite batch does, rather than the nonsense we were doing before to make it like.
So that's not doing nothing. That's doing something. I guess is that the opacity bit?
Well, actually, you know what? I can. It's probably quicker to just show you this. So if I go over to the example effect, so I'll just replace this thing here. So this is where we're doing what you can see on your screen now. If I just change that to color and run, okay, first of all we get this, but now we're taking the color and multiplying it. So if I go to the shader test thing and I change the color of this to be like orange, now we're using that color that we're passing in, and so this becomes orange. Whereas if I change this back to that before, we're ignoring the color argument and we're getting now fancy.
And that's exactly what sprite batch does, because that's how you can like multiply by colors to get tint in any like white sprite when you're using sprite batch. It's doing the same thing.
Exactly, absolutely, exactly correct. So that's more or less what this shader is. Like this shader is pretty much basic effect or sprite batch doing its usual things. So that's all more or less the same. And then this one, the texture sampler, that's the same. And then all we just talked about that, and the pixel shader bit's the same, and the vertex shader bit's very similar. The new stuff, so we've got this vertex shader function, and rather than like explicitly taking like little, argument, return value, we actually want multiple return values is the main thing. So we've got this vertex shader output, and so this is just a struct, and so this should be pretty familiar. And we may as well just do it on the input side as well. So we've got this input here and the return value output, and this is exactly the same. Like this is exactly what you'd expect. You're taking, so this is actually how it happens for the sprite batch as well. Like I skipped over this step. The things that you specify in the vertex declaration, they come in to the input, which gets passed into this vertex shader function, and then we make our own output. And so we're going to multiply the position by this matrix. So this is a bit of global data that we have to set before we use it. So this is part of basic effect will do this for us, but if we were replacing a basic effect, we'd have to actually set this view projection matrix. So you recall that when we were setting when we were over here setting the camera, where'd it go?
I remember, yeah, there's a
we set the world matrix, and we set the view matrix, and we set the projection matrix, and basic effect multiplies that all together and does this for us. So we'd have to do this ourselves. So we get this matrix, and then we multiply our input position by the matrix so that we've got the right, the transform position, and then we just we just pass those through, and so it's done. Yes.
Sorry, yeah. Just that in this line effect too, the view projection's just being declared at the top, but is nowhere. Is that one of those intrinsics, or is that? I mean, you said we'd have to set it ourselves, so I assume it's not.
Yeah. So this is a
4x4 coming from.
This is more or less a global variable. That one there. So, and I'll just show you come back.
I just find it weird that we have to declare it when it's global, but we don't have to declare the intrinsic methods, even though they are also global.
Well, the intrinsic methods are coming from the language.
Right.
Whereas these other things are things that we specify. So if I have an effect, I have one right here. So example effect. So this is just going to be some rubbish code, but example effect dot what do they call it? Parameters. So parameters is actually a I can actually get them by index or by name, and obviously name is a lookup. So that would be view project, and I can save that off like view project equals that. So if I want to do it later on without the lookup, I can go view project dot thingy. In fact, I will.
So if you declare it in the shader, it knows to look for it in the data that's being pushed to it?
Sort of. It basically defines a space in memory that this represents. It's like this is pointing to the space in memory for that shader. And so then when I go, it shouldn't be equals, view project dot set value, and you can see this is an overload with like a whole bunch of types, and so
regular structy thingies. Yeah.
So I have to select the correct type, but so I might have a matrix. I might have a bunch of matrices. I might have a view matrix, and I might have a project matrix, and so I need to set the value, and it would be view times project. And the reason I do this multiplication here, that's unassigned, that's fine. The reason I did the multiplication here is so that I'm not doing it like on the GPU for every vertex, having to multiply view times project, because that's a 4x4 matrix multiplication. I'd rather do that once than like if I have 1,000 vertices, I'd rather not do that 1,000 times on the GPU. So obviously I do it once here. So that's why that's why that's combined as view project in the shader, rather than these two separate things. Make sense?
Right, and and that's the same reason that we were doing all of our math before ahead, so we wouldn't have to recalculate it. Yeah. Okay.
So that's
Okay. Nope, just like I'm good.
Yeah. Good. So and just to finish up, maybe I can give you a quick preview of what we're going to do next time. Where's my effect? Sample effect. So let's see if I can do this. Remember, what I want, I think, is return float 4 text core.x times x y times y. So I've come up with a new shader that's going to be like a black and white thing that's going to draw, what did we get wrong? Incorrect number of arguments. Okay, so I didn't want that. I think I cast it to a float 4. This is, here we go. So you can see I've got this sort of circle effect going on here. And so what I'm doing is x squared plus y squared, which sort of you should remember as like the circle formula. Are you familiar with that?
I am now.
And from memory, I think this is the intrinsic that I want. No, not saturate. Possibly it's 1 minus that. No.
That's cool.
I'm trying to remember exactly what this. No, okay. There's an intrinsic that will do well. Like this is a thing that I can do, and that is, I think, float v equals this, and then I can go if v is greater than 1, return 4 1 1 1 1, else return float 4 0 0 0 0. We'll just store that for later. I think this is right. There we go. So, and then that's a circle. And obviously, if we kept working on this, we could convert that to go on our pretty little lines from last week. So we could look at that next week, or I could just give you the code for that because it's not that exciting, the exact mechanics of how that works. But what we will talk about for sure next week is like what is interesting about that circle formula. So any questions before we finish up?
No, that's good. Brain's a little full from holiday slowness, but yeah, no, it's good. It'll be cool to get those end caps on the circle thing without having to use those sprites. But yeah, it's cool.
Okay, all right. Let's stop recording.